Well, welcome back, and thanks for joining me. Today we're going to talk about different methods of separating mixtures. Now, mixtures are not chemically bonded together, so you don't need to do a chemical reaction in order to separate mixtures. Compounds, on the other hand, are chemically bonded, and the methods I'm going to describe here would not separate compounds. So let's get started. I'll put a few on the list here. A magnet is a really simple way to separate out iron, let's say, from other things. So when you put your materials in the recycle bin, they're going to use a giant magnet to get all the things that are magnetic pulled out. You could easily imagine if you were to hide a paper clip in a bowl of cereal, you could simply put a magnet in to the bowl of cereal and move it around, and you could easily find that little paper clip that was put in there. Alright, if we talk about things like an electromagnet, that's a little bit different. If you have an old automobile that's going to be crushed because it doesn't run anymore, they might just pick that automobile up and then drop it. Now, there's no on-off switch necessarily on the magnet, but what they do is they pass an electric current through the wires, and that induces or creates a magnet. And when the electricity is no longer going through the wires, then the magnet is not formed and it drops the object. So a magnet is one method to separate mixtures. A filter is another one. A filter is one you're pretty familiar with. Maybe you have in biology studied dialysis, where you have people with problems with their blood, so the blood is pumped out of their body, and then it's filtered, and then it's put back in their body. I think of things like sickle cell anemia, things like that. Or maybe you just are going to wash your hands, and there's a little frit, a little filter on the end of your faucet. And the purpose of that is to keep sand out from hitting you or other particulate that might be stuck in your water. Another method is called DECANT. If you can imagine in your head, imagine some dirty, muddy water. And if you allow the dirt in the water to settle down to the bottom, if you have a steady hand, you can pour off the liquid and leave the dirt behind. And what you're doing is called decanting. So it's separating out the mixture without using a filter. Evaporation is another method. Maybe you have seawater, and you pump that water into a container, a large container, and then you let it sit for weeks and weeks and weeks, and the water evaporates, and what you're left with is salt. So that process is evaporation. A centrifuge we'll talk about here, and the rest of these I'm going to kind of let them come up separately. So there's lots and lots of different techniques here. So what we're looking at here is simply a filter. Okay, so you've got here some water or some substance that has something dissolved in it, and the particulate, the particles, are larger than the pores in the filter paper. So when you pour the liquid in, the liquid flows through, and that's called the filtrate, and then you can take out all the solid chunks in there that you're trying to get out. So that's the process of filtration. This is a setup for distillation, and we'll spend more time on that a little bit later in the presentation. Alright, so we've already chatted about if you have a solid and it is maybe dissolved in a liquid and the particles are large enough, you can stop them with a filter. And of course they make different size filters. Another example of this, maybe closer to home, would be your air conditioner. In your furnace there is a filter, and it needs to be changed every 30 to 90 days. And the purpose of that is to take whatever dust is in the air, that's dead skin and dirt and anything else flying around, cat dander, that's in your home, and you don't want that to clog up your furnace, so there's a filter. And then you have to change the filter to get all that yucky stuff out of there. One of my first jobs, my first job was a paper route. I had that for probably 7 years. And then when I was in high school, my junior year, I got a job at the towns water department, and my job was to collect water samples. Now, this is my homage to that. What they called water was wastewater. So you can imagine what the yellow liquid really represents and the brown chunks. I won't have to tell you. But part of my job was to figure out how much dissolved solids was in there. So there's a method to do this where the liquid would be poured into a container, the solids would sink to the bottom, and then we would figure out the percent. This is another method that might work to separate that out. You're going to take a very high quality filter, you're going to pour that raw sewage, that effluent, into the container, and what comes out the bottom is pure water. I've seen these sold before in survival places, survival stores, where they sell you like a straw that has a membrane in it that you can drink very polluted water, and the only thing that will get through the membrane or the filter is pure water. So this is the process of filtration. And again, if we were looking carefully, what we notice is the filter has small little holes in it that allow the water to get through, but not the larger chunks. All right, let's talk about another method called chromatography. Maybe you've done this. Maybe you made a tie-dye shirt in summer camp, right? Where you tie up the shirt and twist it up, and then you add dye to it, and then you let the dye seep out and diffuse into the shirt. Well, that's an example of chromatography. Chroma refers to color, and photography, kind of a picture. Think about photography, right? So a picture of color. Now, that's one way to think about it, but there's other things we could do. If we were in class, I would take a coffee filter, and I would take different markers, a black marker, a red marker, a green marker, and I'd put a few dots on the papers on the filter, and then I'd put it in water, and we would see what happens. I'll show you in just a moment what that might look like. But some other applications of chromatography might be something like DNA testing. Prior to 1990, there was not DNA testing. Nowadays, you think about it, if they find a hair or a fingernail or any amount of your body, they can basically identify you from your DNA. So let me give you a few examples here. The Tomb of the Unknown Soldiers in Washington, D.C., and after World War II, I believe, they took soldiers from each of the branches of the military that had died, and they were unidentified, and they buried them in this tomb. And then they have an honor guard that marches 21 steps down and 21 steps back, like a 21-gun salute. And they do this 24 hours a day, 7 days a week, 365 days a year, to honor those soldiers that have fallen. Now, the interesting thing is, about 10 years ago, a family had done some research, and they believed that their grandfather was entombed in the Tomb of the Unknown Soldiers. And they must have had enough evidence to support this, because the government exhumed the body and tested it, and sure enough, it was their grandfather. Since then, the family asked to have his body removed and buried in a private cemetery. I think if it was my grandfather, I would have probably left him there with a placard to say, here was my grandfather, here's his name, and we've now identified one of the unknown soldiers. Other things you can do with DNA testing, you can do paternity testing, right? A show that I would not advise you to watch might be, Jerry Springer, right? Or there was another one where, and I can't even think of the guy's name right now, had Maury Povich on there, and basically they would take somebody who didn't know, a woman who didn't know who the husband was or the father of their child. They had the child out of wedlock, and of course they would do DNA testing, and they would have 3 or 4 different guys show up on the show. All of them would be tested, and sometimes the first one would say, you are not the father, you are not the father, you are not the father. And then the next episode, they'd have 3 more guys that she was sleeping with. And finally, they'd say, you are the father of this child. At that point, that male is now liable to pay for all the child rearing and the college expenses and everything else for that child. So paternity testing is a very powerful tool, and it involves, again, chromatography. So let's talk about how this might work. So let's pretend that I don't like cats, all right? And let's pretend that there's a crime scene where we find a murdered cat. Ooh. Now, it wasn't me. I'm not even a suspect. But we do some DNA testing where we take the bloody cat hair and we run what's called a gel electrophoresis on that. And we have two different suspects, Greg Giblin and Valerie Wilson. And then we run the cat's DNA. So here's the cat's DNA, at least the relevant part on the chromatography. Here's Valerie Wilson's, here's Greg Giblin's, and here's the bloody cat hair. Now, if you're the expert looking at the bloody cat hair, Greg's DNA, and Valerie's DNA, who would you say did the crime? Well, it looks to me like there's a real strong one here that matches, and these two bands match, and nothing else matches for Valerie, so I think Greg is the one who killed the cat. Now, this is how O.J. Simpson was convicted with DNA evidence, and many, many, many other people. Now, DNA can also cut the other way. It can actually exonerate or free someone from the crime they're accused of committing if the DNA evidence doesn't match. And again, this is an example of separating out a mixture not by doing a chemical reaction, but by physical means. It turns out that if you pass an electric current on the DNA, it will move at a different rate depending on the molecular weight of the components inside. So let's talk about paper chromatography. How would that work? Well, I have a piece of paper and I've bent it up and I have some water in the bottom of my container. And I'm going to go ahead and add some dye, some red dye and maybe some green dye and some black dye. And these might be a pen from a vis-a-vis marker. And then I'm going to place that in the liquid and not touch it. And through capillary attraction, the water is going to move up the paper and it's going to dissolve some of the dyes that make up those colors. And because this isn't a permanent marker, it will actually separate. So when I do that, here's my dyes again, the red, the green, the black. I put that in the water and they start to dissolve and they start to migrate. And what I find is black is actually made from blue and green and red. And green is actually made from blue and yellow. And red has some red and yellow dye. This is more what it would maybe look like after you run it for a while, but it will separate out in very clear bands indicating that you have different components in that mixture. So again, we're separating out different components. Another way to do chromatography is using what's called HPLC. It stands for, depending on who you talk to, high pressure liquid chromatography, high performance liquid chromatography, high priced liquid chromatography. And you have basically a stationary phase, something that's not going to move. It's generally a silica or sand-based material, and it is coated with something that selectively will absorb or hold on to whatever you're injecting in. Then you push a liquid through the column under very high pressure, and that causes the mixture to separate out and move through the column. So if we look at our column, we're looking on the inside, we've got that sand in there, so I'm going to inject some of my mixture in here, and that mixture is made of little smiley faces, little pieces of blue something, some red and some yellow. Let's pretend that's my blood. Okay? The yellow might represent bilirubin. That's what it causes your urine to be yellow and your feces to be brown. It's also, if you're jaundice, why your eyes turn yellow. The whites of your eyes turn yellow if you're not getting that bilirubin out of your body. And as I apply a liquid under high pressure pushing through, what happens is the bilirubin, the yellow, tends to flow more rapidly through the stationary phase. The little smiley faces they go a little bit slower. So at the end I have a detector, and it will detect when the bilirubin comes through, when the red blood cells come through, when the sadness comes through, when I'm feeling blue, and when my joy comes through, when the happiness comes through. So each will come out at a separate time. So you can separate mixtures that are not bonded together, but instead are simply a mixture, either heterogeneous or homogeneous. Column chromatography will separate those out. Now, what you might get if you use column chromatography on some orange juice is you will get what's called a chromatogram. It's the printout. And so here's what it might look like. And so we're separating out the components or parts that are in the orange juice. So it has a little sodium and some potassium and magnesium and iron and calcium. So I might be able to analyze that to see each sample, is it going to have the right mixture of different components. Notice they each come out at a different time, so they can actually be collected and separated. All right, let's talk about distillation. Distillation is using, again, what you might call a still if you lived in Kentucky, right? And this is how moonshiners would have made their moonshine, okay? So in its most basic sense, well, let's go back a little bit and just start to separate mixtures, and then we'll build into that a little bit. So I've got here a Bunsen burner, I've got a ring stand and a wire gauze hole on top of this wire ring, and it's holding up a beaker full of water. So if I heat that up, I could get all the water to boil off. Now in olden days, they maybe would have used this thing called a retort, and you would have put whatever you wanted down this long snout into here, and then you could have heated it up, and it would have heated up, turned to a liquid, hit the glass, condense, that means to cool, and back to a liquid, and then it would collect drip, 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 and you could separate out the mixtures using a retort. Retorts haven't been used in probably 150 years. Now the distillation apparatus looks very similar to the retort. This is the bottom of the retort, and then this is the long neck that you would have seen, except now it can be separated in two pieces. So how this works is, let's assume that I'm making my own alcohol. So I will make my mash, that's basically just maybe water with corn and sugar and yeast. And what happens is the yeast will eat the corn, drink the water, and they'll have a lot of babies in the process, but they'll also excrete out their urine, their waste product. And it turns out that their waste product, that yellow stuff, that's alcohol. So if you are drinking alcohol, you are drinking yeast urine. Yuck. Now, it turns out that water has a boiling point of about 100 degrees Celsius, and alcohol has a boiling temperature significantly less than that, maybe 78 degrees Celsius. So if I have a mixture in here, in my distilling flask, of water and alcohol, if I heat it up slowly, once it gets to 78 degrees, the alcohol will boil. It will go up, and then it moves down this tube where there's an inner tube and an outer tube, and the outer tube is connected to cold water. So there's cold water surrounding the hot gas and the inner tube. And the purpose of this cold water touching the glass that's in contact with the hot gas is to cause it to condense. So this is called the condenser. And then what happens is, the receiving flask, you'll get drip, drip, drip. You'll get pure alcohol, 200 proof, pure alcohol out the other end. And it will continue to put alcohol out here until all the alcohol's gone. And then I can stop collecting, and then the only thing I have left in here is my water. So if you've heard of a still, they're just simply looking at the word distillation, and maybe they're too silly to know the name, but still comes from distillation. If you were to use, let's say, salt water in a still, what would happen is you would boil the water. This time the water will boil first, will hit the condenser, and you'll get pure water out. And salt, because it has a much, much, much higher boiling point, will stay behind. And so this is a way you can separate out salt from water. Distillation is a way that you can separate about any mixture as long as they have a different boiling point. When you're all done then with that, with salt and water, you got your pure water here and your salt sitting over here. All right, when we did that, when we changed salt water into salt plus water, that process of distillation, that was a physical method of separation. There was no chemical change occurring. You can also take water with food coloring in and you can distill it and you will end up with pure colorless water at the end. You can have wastewater, again, water that might have urine in it or other things. If you distill it, you'll have pure, clean, distilled water on the other side. All right, let's pretend that you wanted to separate out sand and salt water. The first thing you might do is you could use a filter to separate out sand from salt. If you were really steady with your hands, you could probably allow the sand to just settle to the bottom, and then what's that called where you pour the liquid off and leave the solid behind? Decant, you're right. So you could either use filtration or decantation to decant that sand and separate out from the salt water. At that point, you would probably need to use distillation, a second physical method, to separate out salt from water. So you could very quickly separate out sand from salt from water using these physical methods. Usually I have you design your own flowchart and then we go in the lab and we practice this skill. So let's kind of look at, if I gave you a mixture that contained sand and salt and had you do this, you might do something like this. You have your mixture. Because I want this thing to be done quantitatively, that means you have to measure the amounts, you would weigh the initial mixture. You'd pour it in some heat resistant container, you'd fill it up with water, and then you'd stir it and let it settle for a minute. What are we trying to accomplish in this first step? Well, what I was trying to accomplish is get the salt to dissolve in the water. Then I would decant off the liquid, that would be the salt water, and I'd have left wet sand. I would then maybe repeat this multiple times because I have sand and maybe there's some more salt in it. So I'd fill it with water, stir it, let it settle, decant, and I would do this maybe a total of 3 or 4 times. Once I've done that, I'm pretty sure I got all the salt out of the water. Then I would evaporate out the water from the salt, and I would have dry sand left. I would weigh the sand, at this point, because the water was already separated out, I would only have sand in water. So I'd evaporate that. I'd be left with my dry sand. I would weigh it, and then I could calculate how much salt was removed by subtracting from that. So this is a flow diagram. Generally, I have you practice writing flow diagrams. We won't do that in lab this year, but I want to just share how that might look to you. All right, let's talk about another method called a centrifuge. Maybe you've been in a carnival and they have that ride that spins around really, really fast. You go in, it's a round kind of room, and then it spins really fast and the floor drops out and you're stuck against the wall, right? That's a giant centrifuge. So it spins the sample very rapidly so that the more dense material goes to the bottom. So let's say that I'm going to go give blood. So they will take my blood. Now, maybe you know this, maybe you've forgotten. Blood is a mixture of red blood cells, serum, and something called the buffy coat or white blood cells. Now, if they take my blood and they put it in a centrifuge and it spins around very rapidly for a few moments, then it will separate out. And if my blood looks like B, then I have plenty of red blood cells. They're going to let me donate. If my blood looks like C, not a lot of red blood cells, then I am suffering from something called anemia. Now, anemia is just low red blood cell count. Oftentimes they'll say you have low iron, right? Women tend to have more issues with anemia. Sometimes they maybe don't eat as much red meat. Sometimes there'll be monthly things that occur with regular intervals of blood loss. Generally, guys are not getting in fights monthly, losing blood regularly, so it tends not to affect males as often. If you know you are anemic, then you should be eating extra dark green leafy vegetables like iron, or like spinach, very high in iron, and or maybe take an iron supplement. It's best to have a blood test done to find out what your actual level is at the doctor's office. If you find you're tired all the time and you look kind of pale and you seem to be getting enough sleep, most likely you're suffering from anemia. So it's a relatively easy thing to fix once you're aware of it. All right, and again, there was no chemical reaction taking place. It was just a rapid spinning, and the centrifugal force caused the red blood cells, because they're denser, to sink to the bottom, and the serum floated on the top. Well, we got some water pouring in a beaker here, and if we look at water, we remember they're sort of stuck together, aren't they, with hydrogen bonding. But the water molecules themselves, they're a compound. We can separate those if we use something called electrolysis, or an electric current. So I've got water molecules here, and if you pass an electric current through it, what happens is the water will separate into, and I'm using this special apparatus called an electrolysis apparatus, and it has here a battery, a direct current battery. It has two electrodes, a cathode and an anode, and when you pass electricity through it, one end becomes positive, one becomes negative, and it rips the water apart, and you end up forming hydrogen and oxygen. Now, it's hard for you to see, but if you put your face really close to the screen, you'll notice that you have only this much oxygen and you have double the amount of hydrogen. It is exactly a 2-to-1 ratio, and that's shown by the equation. 2 waters break down into 2 hydrogens and 1 part water, a 2-to-1 ratio. Now, in this case, it's not a chemical reaction, but we are separating a compound without doing a chemical reaction. This process is again called electrolysis. So the 2 waters turn into 1 diatomic oxygen and 2 diatomic hydrogens. Electrolysis is also used to maybe remove unwanted hair. If you're a male and you have fur all over your back, and when you go to the beach people start screaming something about Sasquatch or something, right? Yeah, it might be embarrassing to you. So you could shave that hair off all the time from your back, but it's only going to grow in thicker and heavier. So if it bothers you enough, I suppose you could have it waxed off, or you could go to the doctor's office and they will use electrolysis, where they'll touch each hair, pass an electric current through, and it will fall off and never grow back. Sometimes women have some unwanted facial hair, and they will use electrolysis for the same process. I don't believe it's a very inexpensive process. It's probably pretty costly, but it is a permanent solution for unwanted, unsightly hair. All right, so here is our electrolysis apparatus. It's a little bit bigger, so you can see that you got 1 part oxygen, 2 parts hydrogen. You can see that a little bit better. Now I'm using direct current. It flows in one direction. If you were to use alternating current, it would make hydrogen and then oxygen, and then it would switch and make oxygen and hydrogen, and you get equal parts, and it would be hard for you to see. That word, obviously, electrolysis, involves electricity, and the word lysis means to split or separate something. Cells can lyse or split. If you take blood cells and put them in too high of concentration of salt water, they will split or lyse. So again, we've looked at that reaction where water, if you pass electricity through it, will form oxygen and hydrogen. Now, in order for this to occur, you have to have a little bit of impurity in the water. The first time I did this demonstration many years ago, I used distilled water. I wanted it to work right, and nothing happened. As soon as you add a drop of any kind of impurity in here, then it starts to work. So I'm saying put a catalyst like an acid in there. That's what that H with a plus charge refers to, as an acid, to carry the electric current through the water. Now, you're like, why do they tell you to get out of a swimming pool when there's a lightning storm? Well, I'll guarantee the swimming pool you're in is not pure water. Little kids have swam there, and people that are too embarrassed to get out of the pool to use the bathroom, they've just gone in the pool. It's not very pure. There's a reason I don't put my face under the water very often in a swimming pool. I'll see if I can link for you a video so you can sort of watch electrolysis, how that happens. I'll try to put that on the site instead of play this video right now, because I think we might have problems if we play it from here. We also have a little setup that looks something like this that I generally do for a demonstration, where again you just hook it up to a battery, and right in front of your eyes you can watch the hydrogen oxygen form. It's pretty cool. We're not going to worry about the half reactions. If you take AP Chem, when we deal with electrochem, we'll deal with that. But for our first year honors course, we simply want you to be familiar with the term electrolysis as a means of separating mixtures. All right, there's some review concepts for you to think about, right? And I won't answer them. I'll let you think about it. Give me 7 examples of physical properties. Describe uses of physical properties. Name 2 processes that are used to separate mixtures. And then you can see the last question. These aren't necessarily test questions. They're just things that in class maybe we would have discussed. All right, well, thanks for joining me. Make sure you're watching the videos. It appears to me that only about half of you are watching the videos when I'm looking at the number of views on YouTube. So please make sure you do your part and watch those videos. Thank you. Bye-bye.